Hello everyone, I am Deepak Paliwal. So in the continuation of the previous lecture, today we will discuss about the sleep systems in case of BCC and the FCC. So let me take pen here. We will discuss about the sleep system in case of BCC and FCC. For sleep systems, we need to understand the what is the closed packed plane, closed packed planes and closed packed direction. So the closed packed plane we find out with the help of what we find out the closed packed plane with the help of planar density. Those planes those planes with the maximum planar density are called as the closed packed plane. Similar for closed packed direction we find out with the help of linear density. So those directions with the maximum linear density termed as closed packed directions. So by one, firstly we will consider the BCC, then we will consider FCC. So firstly we will try to find out the closed packed planes, then we will discuss about the closed packed direction in case of BCC. So let's start. So let me draw a unit cell, BCC unit cell. As we know, in case of BCC unit cell, we have atoms at the corner and atom at the body center position. Okay, so uh, we will calculate the planar density for the 100 plane, then 110 plane, and then 111 plane. Let me draw the 100 plane here. I am drawing the 100 plane. This is, let me highlight here, this is our 100 plane which I shared with the yellow color. I hope you can see this yellow color. So I am also drawing additionally outside this, so outside this unit cell. So here we have 100 plane. The atoms at the 100 plane we have this one. So total how many number of atoms here? We have four number of atom, and each atom is contributed shared between the four unit cell here. So we can, or you can say, the only 1/4 part of this atom present inside the plane. So the each atom is contributing to the 1/4. So total number of atom will be 1 in case of 100 plane. If I want to calculate the area here, so here this is the A. I am considering the latest parameter of this cubic unit cell is A. So the area will be length into breadth. So here A into A, so it will be A square. So our formula to calculate the planar density is equal to number of atom in a plane divided by area of the plane. So this is the common formula for all. With this formula we will calculate the planar density. Now we have this, the number of atom. So just we will put this into the formula. So we have one atom at the 100 plane, and we have area is A square. Now we will calculate for the 110 plane. So let me draw 110 plane in the unit cell, then I will take this out from this unit cell. So this is the shaded plane is 110 plane. So let me take this 100 plane outside this. You can see clearly here the difference between 100 plane, difference between the 100 plane which I have shown here and the 110 plane I have shown here. So I have shown that this length is longer compared to this length, whereas in the case of 100 I shown this length and this length are the similar, because this is the this is a square. while this is a rectangle. You can see here this length is longer as compared to this length. That's why in my representation also I am showing that this length is larger and this length is smaller. So now coming again, here is a one more atom at the center. So firstly we will calculate the number of atom, which is equal to each corner atom will contribute 1/4 to the unit cell, and we have 4 number of atom, plus we have one body centered atom and it is solely belong to the or completely belong to the 110 plane. So we have 1, so total number of atom will be 1 plus 1, this is 2. And the area, for the area calculation we know this is a, and from here this is also a, so we can calculate with the help of Pythagoras theorem here. So a square plus a square will be the length of particular this particular line. So we have this line length is root 2a, so multiplying with a into root 2a, that would be the area for your 110 plane. Now planar density, we have written here a formula. So here we have to put the number of atom in the plane and then area of the plane. So now we will put 2 is the number of atom and this will be root 2a square. So that would be root 2a square is your planar density for planar density for 110 plane, and this was the planar density for 100 plane. Now we will calculate for 111 plane. So let me highlight the 111 plane maybe with the different color. Here we have, this is our 111 plane. Let me draw some hatching here. So the triangular shape which we are observing in a unit cell is our 111 plane. Actually it is an octahedral plane. So this is the 111 plane. How we can, let me draw outside the unit cell. So we have atom at the corners. Okay, only we have atom at the corner only, and this body centered atom does not lie in this plane. In the upcoming slides I will show why this atom does not lie inside this plane. Actually if we measure the distance of this plane and this atom from the corner, it comes out that this atom does not lie inside this plane. Or we can say like we have a formula HL plus HL plus HU plus KV plus LW. If it is equal to 0, then that particular atom will lie into the, like what I am saying. Let me write this formula: HU plus KV plus LW. If it is equal to 0, then the whatever atom you are considering, this UVW, don't be confused. We are not talking here with the direction. Okay, we are just talking about the coordinates of atom. So the coordinate of body centered atom is 1 by 2 1 by 2 1 by 2. Okay, and your plane is 1 1 1. Now let me put into the equation 1 into 1 by 2 plus 1 into 1 by 2 plus 1 into 1 by 2. So it will be 3 by 2. So it is not equal to 0. That's why this body centered atom does not lie in 111 plane. Okay, so let me erase it. Okay, it does not lie in 111 plane, as I have mentioned that it does not lie in that particular plane. We have seen quantitatively as well. Let me rub it off. Now we will see number of atom. So each corner atom contribute 1 by 6th to this plane. So we have 3 number of atom here. So total number of atom here 1 by 2 in case of 111 plane. Okay, Now we will calculate the area. We know this side is belongs to this side. Okay, so this is root 2a, again this is root 2a, again this is root 2a. So now we want to put into the formula. If you know the equilateral triangle area formula, then you can directly put. Otherwise what you can do is just put a perpendicular here. Okay, just try to calculate this x value. So firstly I am calculating the x value here. Let me erase this one first. Firstly we will calculate the x value, and then we can make the triangle formula directly. So x value will be, this is root 2a by 2. So how I can calculate? Root 2a square minus a by root 2 square. So 2a square minus a square by 2. So this is 3a square by 2 x square. So x will be like this, again root 3 by 2a. Now we can put in the area formula, which is 1 by 2 into base into height. So 1 by 2, our base is equal to root 2a into h is our x. Okay, so this is root 3 by root 2 a. So root 2 will be cancelled by root 2. So this will be root 3 by 2 a square. Okay, so now root 3 by 2 a square, I am writing it here. Actually I want to compile these results in a single slide so that we can arrange our results. So now planar density for 111 plane, we can calculate the planar density. Number of atoms, how many number of atoms we have? 1 by 2 divide by area is root 3 by 2 a square. So we will divide root 3. So now maybe let me write with a different color so that we can distinguish. So here what we have, 1 by root 3 a square. Okay, so now here we have got the results. So the closest packed plane is 110. So what we can say, the planar density of 110 plane is greater than the planar density of 100, then planar density of 111 plane. So the closest packed plane in case of BCC is 110. Actually the BCC is not the closest packed unit cell actually, but in the configuration of BCC we have closest packed plane is 110. Let me now in the next slide we will discuss about what is the closest packed direction in case of BCC and how we can calculate the linear density of direction. That we will learn in the next slide. So to calculate the linear density, let me first draw a unit cell of BCC. Then we will take out the required directions from this. So we have atoms at the corner. Now let me show a BCC. Okay, now again what we will do, we will do calculate the linear densities for 100, 110, 111. Okay, so as we know, the linear density formula is linear density is equal to number of atoms in a line or on the line divided by length of line. Okay, so let me take out the 100. We show the line 100 like this bracket, direction shown by this bracket. This bracket shows the family of the directions. So firstly we will have 100, this is 100. Okay, we can say 100 is like this is our actually in terms of 100. These all are the family of 100. Okay, these all directions are families of 100. Okay, so the actual 100 is this. So let us take out this 100 direction, and we know it will have two atoms here. Okay, each atom is contributing 1 by 2 to this length. So the number of atom is equal to 1 by 2 into 2, and length of line, we know this lattice parameter is a, so the length of line is a. So now linear density, I am calling this linear density for 100 is equal to number of atom, which is equal to 1. Okay, which is equal to 1 divided by a. So the linear density for 100 is 1 by a. Okay, now we will calculate the linear density for 110. So 110 direction is, this one is 110 direction, this one is 110 direction. Actually all this direction belongs to the family of 110 direction. Okay, so this is the 110 direction. So now let me take out the 110 direction. Again it will have two atoms, each atom will contribute number of atoms, each atom is contributing 1 by 2, and we have two number of atoms, so total number of atom is 1. But the length, we know this length will be this is a, this is a, so this length will be root 2a, this length will be root 2a. So the length of line is equal to root 2a. So linear density for 110 plane or 110 direction, I called it plane, but actually we are calculating the linear density for a direction. So the linear density for 110 direction is equal to 1 divided by root 2a. Now similarly we will calculate linear density for 111. So let me show what is the 111 direction here. 111 direction, so this is the 111 direction. So let us take out this 110 direction. Here we have atoms here, consider these as atoms. So from the visualization part also we can say this is the closest packed direction, because here the number of atom is more, or even is closely packed. Here is only one atom, here is only one atom, here we can say this is the two atom. How we can say the number of atom is equal to 1 by 2, the corner atom which is contributing half to this line, and there are two atoms, and there is a one single atom which belongs completely to this line, this is called 1. Okay, so there will be total two number of atom, and the length of line is equal to root 3a. How I can say root 3a? Root 3a. So now consider this triangle. Let me mark with different let me call it a, b, c. Okay, let me take out this triangle for your simplicity. So this is a, this is b, this is c. So this direction is, length is root 2a, and this one is a, so this one will be 2a square plus a square under root, so 1 and 2, that will be 3, so that will be root 3a. Okay, so now linear density will be, linear density for 111 direction will be 2 divided by root 3a. Now carefully analyze which one has the largest linear density. So you can say linear density of 111 is largest, and second one is linear density of 100, and least linear density in case of least linear density in case of BCC is 110 direction. Okay, so for plane we got planar density maximum for 110 plane, okay, and linear density maximum for 111 direction, okay, in case of BCC. So next part of this lecture we will see the sleep systems or closed peg plane and closed peg direction for the FCC. Actually, one more additional information I want to give. Actually, here is the in case of BCC we have closed peg direction, but there is no nothing like closed peg plane. In case of BCC, we have 110, we have 112, we have 123 planes where sleeps can occur, or sleep can occur in case of BCC in 110, 112 and 123, and there is one closed peg direction which is 111. So we will meet in the next lecture where we will discuss about the sleep systems of FCC material. Thank you.